Hello there, and welcome to a journey through the extraordinary forces that shape our planet. Tonight, we'll explore the awesome power of Earth itself, the trembling ground beneath our feet, the restless atmosphere above us, and the rolling waters that cover most of our world. These are forces both destructive and creative, terrifying yet essential to the very existence of life as we know it. Natural disasters can seem like chaos, moments when the planet reminds us of our fragility, but they are also part of Earth's story, woven into the fabric of geology, weather, and time itself. Earthquakes reshape continents, hurricanes redistribute heat across oceans, volcanoes build new land from molten rock. Even in their violence, these phenomena follow patterns, obey laws, and carry within them the seeds of renewal. If you find comfort in understanding the world around you, I invite you to settle in, let your breathing slow, and allow these stories of Earth's power to carry you into calm. There is something deeply soothing about perspective, about seeing how even the mightiest forces are part of a larger cycle. For now, all you need to do is rest and let the quiet strength of our planet's story unfold. Let's begin. Earthquakes, the restless Earth, the ground beneath us is always moving. The solid Earth feels stable, unchanging beneath our feet. Yet, in truth, it is in constant motion. The ground we walk upon is part of massive tectonic plates, slabs of rock dozens of miles thick, that float atop the semi-molten mantle below. These plates drift slowly, sometimes converging, sometimes pulling apart, sometimes grinding past one another. The motion is usually imperceptible, measured in centimeters per year, about the rate your fingernails grow. But the forces involved are immense, building pressure over decades or centuries until the rock can no longer hold, and then it breaks. That sudden release of energy is an earthquake. The ground lurches, shifts, and settles into a new position. What felt permanent was only temporary. The Earth reminds us that nothing stays still forever, that change is written into the very foundation of our world. Most earthquakes are too small to feel. Every day, thousands of earthquakes occur around the planet. The vast majority are so minor that only sensitive instruments detect them. These tiny tremors, called microseisms, happen constantly as tectonic plates adjust and settle. They cause no damage, trigger no alarms, and pass unnoticed beneath our cities and forests. Even earthquakes strong enough to rattle dishes or sway chandeliers are relatively common, happening somewhere on Earth every few hours. The seismic activity we fear, the destructive, ground-splitting quakes, are rare by comparison. Yet even the smallest tremor is part of the same process, the same slow dance of continental plates. In a way, these countless small earthquakes are a relief valve, releasing energy gradually rather than all at once. They remind us that Earth is always adjusting, always balancing forces we cannot see. Seismologists measure earthquakes on multiple scales. For over a century, scientists have worked to quantify the strength of earthquakes. The Richter scale, developed in the 1930 seconds, was the first widely used measurement, assigning numbers based on the amplitude of seismic waves. But modern seismology has moved beyond it to more precise measures like the moment magnitude scale, which accounts for the total energy released. These scales are logarithmic, meaning each whole number represents a 10-fold increase in amplitude and roughly 32 times more energy. A magnitude 5 earthquake might crack walls and topple shelves. A magnitude 7 can level buildings and reshape landscapes. A magnitude 9, the highest ever recorded, unleashes energy equivalent to thousands of nuclear bombs. Yet all of these events follow the same physics. governed by the same forces of friction and stress within the Earth's crust. To measure them is to bring order to chaos, to find patterns in what seems random. The deepest earthquakes occur hundreds of miles below the surface. We often imagine earthquakes happening near the surface, where we feel their effects most dramatically. But some occur deep within the Earth, hundreds of miles down, where tectonic plates plunge into the mantle in zones called subduction zones. These deep focus earthquakes can be extremely powerful, though their effects at the surface are often muted by the distance the seismic waves must travel. At such depths, rock behaves differently. The immense pressure changes its properties, making it more plastic, more prone to deformation rather than brittle fracture. Yet even here, stress can build and release suddenly, sending shock waves rippling through the planet. These deep tremors remind us that Earth's interior is not static, but a realm of slow currents and immense forces, hidden from view, but always at work. The longest recorded earthquake lasted over 10 minutes. Most earthquakes are mercifully brief, their shaking lasting only seconds or perhaps a minute. But on the 11th of March, 2011, when a massive quake struck off the coast of Japan, the shaking continued for between 4 and 6 minutes in many areas. For those experiencing it, time seemed to stretch unbearably. Buildings swayed, roads buckled, and the ocean itself began to retreat from the shore, pulled back before the tsunami that would follow. The duration of an earthquake depends on the size of the rupture. A small fault might slip in a second, but when hundreds of miles of fault line move simultaneously, the energy takes much longer to release. The 1960 Valdivia earthquake in Chile, the most powerful ever recorded at magnitude 9.5, ruptured a fault zone over 600 miles long. The ground shook for approximately 10 minutes in some locations. To imagine such prolonged violence is to understand the scale of forces our planet can unleash. Aftershocks can continue for years after a major quake. When a large earthquake occurs, it does not simply end. The initial rupture creates new stresses in the surrounding rock, and the crust must adjust to its new configuration. This adjustment comes in the form of aftershocks, secondary earthquakes that follow the main event. Some aftershocks are nearly as powerful as the original quake, capable of causing additional damage to structures already weakened. Aftershocks follow predictable patterns. They are most frequent in the hours and days immediately following the main shock, then gradually decrease over weeks, months, or even years. The largest aftershocks typically occur closest to the original rupture zone. Seismologists use statistical models to estimate how long aftershocks will continue, helping communities know when it might be safe to rebuild. But the Earth takes its time settling, and patience is required. Animals sometimes behave strangely before earthquakes. For centuries, people have reported unusual animal behavior before earthquakes strike. Dogs barking frantically, birds abandoning their nests, horses refusing to enter stables, snakes emerging from hibernation in winter. While much of this remains anecdotal, scientists have investigated whether animals can sense precursors to earthquakes that humans cannot detect. Some researchers believe animals may be sensitive to subtle ground vibrations, changes in groundwater levels, or electromagnetic anomalies that precede major ruptures. Other explanations are simpler. Animals may simply react to the first, unnoticed tremors that humans miss, the initial P waves that travel faster than the more destructive S waves. Regardless of the mechanism, these observations hint at connections between living systems and geological processes, reminders that we are not separate from the Earth, but deeply embedded in it. Earthquake lights are a rare and mysterious phenomenon. On rare occasions, witnesses report strange lights in the sky, before, during, or after earthquakes. These earthquake lights, or EQLs, appear as flashes, glows, or luminous columns rising from the ground or hovering in the air. Historical accounts describe them in various forms: blue flames dancing on hillsides, orbs floating above fault lines, or aurora-like displays rippling through the atmosphere. Scientists remain uncertain about their cause. Some theories suggest they result from electrical charges generated when rocks fracture under stress, creating piezoelectric effects that ionize the air. Others point to the release of gases that might luminesce. Whatever their origin, earthquake lights remain one of the more enigmatic aspects of seismic events, a reminder that even well-studied phenomena can still surprise us. The Pacific Ring of Fire accounts for most of the world's earthquakes. If you trace a line around the Pacific Ocean, marking the edges of the Pacific Plate, you outline a region of extraordinary geological violence. This boundary, known as the Ring of Fire, is where numerous tectonic plates converge, creating subduction zones, volcanic arcs, and fault systems that produce roughly 90% of the world's earthquakes and 75% of its active volcanoes. Countries along this ring, Japan, Indonesia, the Philippines, New Zealand, Chile, Alaska, and the western coasts of North and South America, live with constant seismic risk. But this same geological activity has shaped their landscapes, building mountain ranges, creating fertile volcanic soils, and forming the islands that millions call home. The Ring of Fire is both a zone of destruction and creation, where the Earth's dynamic nature is most evident. Some faults can produce earthquakes, hundreds of miles from plate boundaries. While most earthquakes occur along plate boundaries, some happen in the middle of continents, far from any obvious tectonic activity. These intraplate earthquakes can be particularly devastating because they occur in regions unaccustomed to seismic risk, where buildings are not designed to withstand shaking. The New Madrid earthquakes of 1811 to 1812, centered in what is now Missouri, were among the most powerful in North American history, yet they occurred more than 1,000 miles from the nearest plate boundary. The causes of intraplate earthquakes are still debated. Some may result from ancient fault lines being reactivated by changes in stress patterns. Others might be triggered by the slow rebound of the crust after the weight of glaciers from the last ice age was removed. Whatever their cause, they remind us that the entire planet's surface is subject to forces we are only beginning to understand. Earthquake early warning systems can provide seconds of notice. Modern technology has given us a precious gift: a few seconds or minutes of warning before the most destructive earthquake waves arrive. Early warning systems detect the initial, less harmful P waves that travel faster through the Earth, then automatically send alerts that arrive before the slower, more damaging S waves and surface waves. Those extra seconds can allow trains to brake, surgeries to pause, and people to take cover. Japan, Mexico, and California have implemented such systems with varying degrees of success. While seconds may not seem like much, they can mean the difference between life and death, between a safely halted train and a derailment, between being caught in an elevator or reaching safety. These systems represent humanity's attempt to work with the Earth's rhythms rather than simply being at their mercy. The San Andreas Fault will eventually produce the Big One. In California, the phrase, "the Big One," refers to the anticipated major earthquake along the San Andreas Fault, a strike-slip boundary where the Pacific Plate grinds past the North American Plate. Sections of this fault have been locked for over a century, accumulating stress that will eventually be released in a powerful earthquake. Seismologists don't know exactly when it will occur. Earthquake prediction remains beyond our capabilities, but they know it will happen. When it does, the shaking will be felt across a vast region. Buildings will collapse, infrastructure will be damaged, and thousands of lives will be disrupted. Yet California has spent decades preparing, enforcing strict building codes, conducting earthquake drills, and stockpiling emergency supplies. The big one is inevitable, but its impact can be mitigated through preparation. In this way, even certain disaster becomes manageable. Ancient earthquakes have left visible scars on the landscape. The earth remembers. Long after the shaking stops and the damage is repaired, the landscape itself bears witness to past earthquakes. Fault scarps, steep cliffs created when one side of a fault rises relative to the other, can remain visible for thousands of years. Offset streams, where rivers suddenly jog to one side, mark places where faults have slipped repeatedly over time. In trenches dug across fault lines, geologists find layers of soil that have been displaced, each layer representing a separate earthquake in the distant past. By studying these features, scientists reconstruct the seismic history of a region, identifying patterns and estimating when the next major earthquake might occur. These ancient scars are a form of geological memory, the Earth's way of recording its own tumultuous past. They tell us that what we experience today is part of a cycle stretching back millions of years. Submarine earthquakes can trigger devastating tsunamis. When an earthquake occurs beneath the ocean, particularly in a subduction zone where one plate dives beneath another, the seafloor can suddenly lurch upward or downward by several meters. This displacement pushes the entire column of water above it, creating waves that radiate outward in all directions. In deep water, these tsunami waves travel at jet speeds, up to 500 miles per hour, but remain relatively low in height, passing beneath ships unnoticed. As they approach shallow coastal waters, however, physics takes over. The waves slow down, but grow taller, sometimes reaching heights of 100 feet or more. They strike the shore not as a single breaking wave, but as a rapid rise in sea level, a wall of water that inundates everything in its path. The 2004 Indian Ocean tsunami killed over 230,000 people across multiple countries. The 2011 Tonso-Hoku tsunami devastated the coast of Japan and triggered the Fukushima nuclear disaster. These events remind us that earthquakes beneath the sea can reach far beyond their epicenters. The largest earthquake ever recorded struck Chile in 1960. On the 22nd of May 1960, the Earth unleashed its most powerful earthquake in recorded history. The Valdivia earthquake, centered in southern Chile, registered a magnitude of 9.5 on the moment magnitude scale. The rupture zone extended for over 600 miles along the Chilean coast, and the shaking was felt as far away as Hawaii. In some areas, the ground rose by several meters. In others, it subsided, permanently flooding coastal towns. The earthquake triggered landslides that dammed rivers, creating lakes that later burst and caused catastrophic flooding. It also generated a tsunami that crossed the Pacific Ocean, causing deaths and damage in Hawaii, Japan, the Philippines, and as far away as New Zealand. The total death toll exceeded 5,000, with millions left homeless. Yet even this extraordinary event was simply the release of stress that had been building for centuries along the boundary between the Nazca and South American plates. Some cities have been built directly on active fault lines. Human settlement often ignores geological reality. Cities arise where geography favors them, near water, at crossroads, in fertile valleys regardless of seismic risk. San Francisco sits astride the San Andreas Fault. Los Angeles sprawls across multiple active faults. Tokyo lies on the junction of 4 tectonic plates. Istanbul straddles the North Anatolian Fault. These cities cannot move, so they must adapt, building earthquake-resistant structures and planning for inevitable disasters. The challenge is immense. Older buildings remain vulnerable, and the cost of retrofitting entire cities is staggering. Yet progress continues, driven by the knowledge that the next major earthquake is not a matter of if, but when. In these cities, the geological past and human present exist in uneasy balance. Each earthquake a reminder of the bargain we've made to live in places of natural beauty and economic opportunity despite the risks. Earthquakes can trigger other earthquakes across vast distances. The stress changes caused by a large earthquake don't remain localized. They can propagate through the Earth's crust, increasing or decreasing pressure on distant faults. This means a major quake in one location can trigger earthquakes hundreds or even thousands of miles away, particularly on faults already close to failure. These triggered earthquakes can occur within minutes, days, or even years after the initial event. Scientists have observed correlations between earthquakes on opposite sides of the planet, though the mechanisms remain debated. Some evidence suggests that seismic waves from a major earthquake can cause distant faults to slip slightly, while deep, slow-traveling waves might alter stress patterns across vast regions. The Earth's crust, it seems, is not a collection of isolated fault systems, but an interconnected network, responsive to disturbances across great distances. The oldest known earthquake records come from ancient China. Humans have been recording earthquakes for millennia. The oldest systematic records come from China, where imperial astronomers and court officials documented seismic events as far back as 1831 BCE. These ancient records describe shaking, damage, and unusual phenomena, providing modern seismologists with valuable historical data. By analyzing these accounts, scientists can identify patterns of seismicity stretching back thousands of years, far longer than instrumental records allow. Other cultures also preserved earthquake memories. Greek and Roman historians described major quakes in the Mediterranean. Japanese records detail centuries of seismic activity. Indigenous oral traditions around the world contain accounts of the earth shaking, mountains rising, and the sea rushing inland. These records remind us that earthquakes have always been part of human experience, shaping societies, toppling empires, and leaving marks on collective memory. Earthquakes have shaped human history and civilization. Throughout history, earthquakes have altered the course of civilizations. The ancient city of Pompeii had been damaged by an earthquake 17 years before Vesuvius erupted in 79 CE. Constantinople, capital of the Byzantine Empire, suffered numerous destructive quakes that weakened its defenses and economy. The 1755 Lisbon earthquake killed tens of thousands and sparked philosophical debates about divine providence and natural law that influenced Enlightenment thinking. In more recent times, the 1906 San Francisco earthquake reshaped American building practices and emergency response. The 1995 Kobe earthquake in Japan led to advances in seismic engineering and disaster preparedness. The 2010 Haiti earthquake exposed the vulnerability of impoverished nations to natural disasters. Each major earthquake forces societies to reckon with their vulnerabilities, leading to changes in construction, planning, and policy. In this way, earthquakes continue to shape not just landscapes, but human institutions and thought. Slow earthquakes release energy over days or weeks, Not all earthquakes are sudden, violent ruptures. Some faults slip slowly, releasing their accumulated stress over days, weeks, or even months. These slow slip events, or silent earthquakes, occur primarily in subduction zones, where the plates are not completely locked. They release the same amount of energy as a traditional earthquake, but do so gradually, producing little to no felt shaking. Scientists discovered slow earthquakes relatively recently, using sensitive GPS instruments that can detect minute movements of the Earth's surface. These events are now recognized as an important part of the earthquake cycle, potentially influencing when and where more traditional earthquakes occur. The discovery of slow earthquakes has changed our understanding of fault behavior, revealing that the boundary between constant motion and sudden rupture is more complex than previously thought. Volcanoes, mountains of fire. Volcanoes are windows into Earth's interior. Beneath the solid crust we inhabit lies a realm of intense heat and pressure. The mantle, extending nearly 2,000 miles below the surface, is composed of rock so hot it flows like thick honey over geological timescales. Volcanoes are the places where this hidden world breaks through to the surface, where molten rock, gases, and ash emerge into the open air. They are windows into the Earth's interior, revealing conditions and materials that otherwise remain forever hidden from view. Every eruption brings fragments of the deep Earth to the surface. Geologists study these materials to understand the composition and behavior of the mantle and crust. Volcanic rocks contain crystals that formed at great depths, mineral assemblages that reveal temperature and pressure conditions miles below. In this way, volcanoes are not just dangerous mountains, but natural laboratories, offering insights into processes we can observe in no other way. There are about 1,500 active volcanoes on land across the continents and islands of our planet. Approximately 1,500 volcanoes are considered active, meaning they have erupted within recorded history or show signs of unrest. Of these, about 50 to 70 erupt each year, though most eruptions are relatively minor, producing small lava flows or ash plumes that pose little threat beyond their immediate vicinity. The distribution of volcanoes is not random. They cluster along tectonic plate boundaries, particularly in the Ring of Fire, encircling the Pacific Ocean. But volcanoes also exist in the middle of plates, above hotspots where plumes of abnormally hot mantle rise from great depths. The Hawaiian Islands formed this way, as the Pacific Plate drifted over a stationary hotspot, creating a chain of volcanic islands stretching across thousands of miles of ocean. Each volcanic island represents a moment in geological time when the hotspot punched through the crust to build a new mountain. Volcanic eruptions are classified by their explosiveness. Not all eruptions are alike. Some volcanoes ooze lava gently, producing flows that creep along the ground at walking pace. Others explode with devastating violence, hurling rock and ash miles into the atmosphere. Volcanologists use the Volcanic Explosivity Index, or VEI, to classify eruptions on a scale from 0 to 8. A VEI 0 eruption might be a quiet lava flow from a Hawaiian volcano. A VEI 8, the highest rating, represents a super eruption capable of altering global climate. The explosiveness depends on the magma's properties, particularly its silica content and gas content. Low silica magma is runny and allows gases to escape easily, producing gentle eruptions. High silica magma is thick and traps gases, creating pressure that eventually explodes violently. The difference between these types determines whether a volcano builds a broad shield shape or a steep, potentially deadly stratovolcano. The most explosive eruptions can inject ash into the stratosphere, When a volcano erupts with extreme violence, it can send columns of ash and gas tens of miles into the atmosphere, punching through the troposphere into the stratosphere, where commercial jets fly. At these altitudes, ash and sulfur dioxide can remain suspended for months or years, carried around the globe by high-altitude winds. This volcanic material reflects sunlight back into space, cooling the planet's surface. The 1991 eruption of Mount Pinatubo in the Philippines injected about 20 million tons of sulfur dioxide into the stratosphere, causing global temperatures to drop by about 0.5 degrees Celsius for several years. The 1815 eruption of Mount Tambora in Indonesia was even more powerful, leading to the year without a summer in 1816, when snow fell in New England in June, and crop failures caused widespread famine in Europe and North America. These eruptions remind us that volcanoes don't just affect their local areas, but can have planetary consequences. Volcanic ash is not ash at all, but tiny fragments of rock. Despite its name, volcanic ash is not the powdery residue of combustion. It consists of tiny fragments of volcanic glass and rock, created when magma is blasted apart by explosive eruptions. These particles are sharp and angular, with jagged edges that can damage engines, contaminate water supplies, and irritate lungs. When inhaled, volcanic ash can cause respiratory problems, and when it accumulates on roofs, its weight can cause buildings to collapse. Ash clouds from eruptions pose serious hazards to aviation. Jet engines can ingest the ash, which melts in the high temperatures inside the engine, then solidifies on cooler components, potentially causing engine failure. The 2010 eruption of Eyjafjallajökull in Iceland grounded air traffic across Europe for days, stranding millions of passengers and demonstrating how even a relatively modest eruption can disrupt modern life across an entire continent. Lava flows can move surprisingly quickly. We often imagine lava as a slow-moving ooze, giving people plenty of time to evacuate. In many cases, this is true. Thick, viscous lava flows might advance only a few meters per hour, allowing observers to walk alongside them safely. But under certain conditions, lava can move much faster. Low-viscosity basaltic lava can rush down slopes at speeds exceeding 30 miles per hour, especially in channels or tubes that insulate the molten rock and keep it fluid. Historical accounts describe lava flows overtaking fleeing villages. In Hawaii, where basaltic eruptions are common, authorities carefully monitor lava flow directions, predicting which communities might be threatened. The unstoppable nature of lava is both mesmerizing and terrifying. No barrier can hold it back for long. It consumes everything in its path: forests, roads, buildings, reducing them to ash and then burying them beneath solid rock. Some volcanoes produce blue flames that burn at night. In a few rare places, volcanoes produce one of nature's most surreal spectacles: electric blue flames that dance across the ground and flicker in the darkness. This phenomenon occurs at Kawah Ijen volcano in Indonesia, where sulfur-rich gases emerge from the earth and ignite upon contact with air. The flames themselves are pale blue, nearly invisible in daylight but stunning after dark, casting an eerie glow over the volcanic landscape. Miners work in these conditions, extracting sulfur that condenses from the gases and hardens into yellow deposits. They carry the heavy blocks on their backs down the mountain, working in toxic fumes and intense heat for minimal pay. The blue flames are beautiful from a distance, but represent a deadly environment up close, a reminder that many natural wonders come with hidden dangers. Volcanic lightning creates spectacular displays during eruptions. During explosive eruptions, volcanic plumes can generate their own lightning. This phenomenon occurs when ash particles collide within the eruption column, transferring electrical charge. As positive and negative charges separate, the voltage difference grows until lightning bolts arc through the ash cloud, creating spectacular displays of nature's power, meeting power. Photographs of volcanic lightning show jagged bolts, illuminating vast plumes of ash, backlit by the glow of molten rock below. The effect is otherworldly, combining the fury of a thunderstorm with the violence of an eruption. Scientists study volcanic lightning to better understand eruption dynamics, as the characteristics of the electrical discharge can reveal information about the size and composition of ash particles being ejected. Pompeii was buried in hours, preserving daily life in volcanic ash. On August 24, 79 CE, Mount Vesuvius erupted with devastating force, burying the Roman cities of Pompeii and Herculaneum under layers of ash and pumice. Pompeii was buried so quickly that the city was frozen in time, preserving buildings, artwork, and even the forms of victims who died in the disaster. Excavations beginning in the 18th century revealed an extraordinarily detailed snapshot of Roman life at the height of the empire. The eruption proceeded in stages. First, pumice rained down, accumulating several feet deep. Many residents fled, but those who stayed or took shelter in buildings were later killed by pyroclastic flows, fast-moving avalanches of hot gas and rock that swept down from the volcano, instantly incinerating everything in their path. The heat was so intense that it caused victims' brains to boil and vaporize, as recent forensic studies have discovered. Pompeii stands as both an archaeological treasure and a sobering reminder of volcanic power. Pyroclastic flows are the deadliest volcanic hazard. Of all the dangers volcanoes present, pyroclastic flows are perhaps the most lethal. These are avalanches of superheated gas, ash, and rock fragments that race down the slopes of volcanoes at speeds exceeding 100 miles per hour, with temperatures reaching 1,000 degrees Celsius or more. They hug the ground, flowing like fluids through valleys and over obstacles, incinerating and burying everything in their path. Pyroclastic flows can travel for miles from their source, and there is essentially no way to outrun them once they begin. The 1902 eruption of Mount Pelée on the Caribbean island of Martinique produced a pyroclastic flow that destroyed the city of Saint-Pierre, killing all but 2 of its approximately 30,000 inhabitants in minutes. One survivor was a prisoner, protected by the thick walls of his cell. The city was obliterated, reduced to charred ruins beneath a blanket of volcanic debris. Lahars are deadly mudflows, triggered by volcanic eruptions. When volcanic eruptions melt snow and ice on a volcano's summit, or when heavy rains saturate loose volcanic deposits, the result can be a lahar, a fast-moving mudflow composed of water and volcanic debris. Lahars have the consistency of wet concrete and can travel at highway speeds, following river valleys for tens of miles from the volcano. They bury everything beneath thick deposits of mud and debris. The 1985 eruption of Nevado del Ruiz in Colombia melted glacial ice, generating lahars that traveled more than 30 miles down river valleys. The town of Armero, home to 29,000 people, lay in the path of one of these flows. Most of the town's residents were asleep when the lahar arrived at night, burying the community beneath several meters of mud and killing more than 23,000 people. Lahars can occur even during small eruptions and can strike areas far from the volcano itself, making them particularly insidious hazards. Calderas form when volcanoes collapse after massive eruptions. The most powerful volcanic eruptions don't just build mountains, they destroy them. When a volcano expels enormous volumes of magma in a super eruption, the chamber beneath can empty partially or completely. Without support, the overlying rock collapses into the void, creating a massive depression called a caldera. These features can be miles across, ringed by steep cliffs that mark where the volcano once stood. Crater Lake in Oregon occupies a caldera formed about 7,700 years ago when Mount Mazama erupted and collapsed. The caldera filled with water over millennia, creating one of the deepest and clearest lakes in North America. Yellowstone National Park sits within a caldera nearly 50 miles across, the remnant of a super eruption 640,000 years ago. Calderas are both beautiful and ominous, reminders of the incredible forces that created them and that might activate again someday. Yellowstone is one of the world's largest supervolcanoes. Beneath Yellowstone National Park lies one of the planet's most powerful volcanic systems. The Yellowstone hotspot has produced 3 super eruptions over the past 2.1 million years, each expelling more than 1,000 cubic kilometers of material. The most recent occurred 640,000 years ago, covering much of North America in ash and altering global climate for years. Today, the park's geysers, hot springs, and bubbling mud pots are surface expressions of the massive magma chamber still present below. The possibility of another super eruption captures public imagination, but scientists emphasize that such events are extremely rare and that the current signs do not suggest one is imminent. Yellowstone's ground rises and falls as magma moves below, and small earthquakes are common, but these are normal for such a system. Monitoring continues, and while another super eruption will likely occur someday, it could be tens of thousands of years in the future. The Earth operates on timescales that dwarf human experience. Some islands are entirely volcanic in origin. Many of the world's islands, particularly those in the Pacific, are entirely volcanic. They began as underwater volcanoes that grew tall enough to break the ocean's surface, then continued erupting until they formed substantial land masses. The Hawaiian Islands are perhaps the most famous example, created as the Pacific Plate moved over a hotspot, building a chain of volcanic islands, from the oldest, now eroded and submerged, to the youngest, the Big Island of Hawaii, which is still actively growing. Iceland sits atop the mid-Atlantic ridge, where 2 tectonic plates are pulling apart. Volcanic activity continuously creates new crust, building the island from both above and below the sea. Indonesia's thousands of islands are mostly volcanic, formed in the subduction zone, where the Indo-Australian plate dives beneath the Eurasian plate. These islands would not exist without volcanism. They are quite literally the Earth building new land from the depths. Volcanic soil is among the most fertile on Earth. For all their danger, volcanoes bring gifts. The ash and lava they produce weather over time into some of the richest soil on the planet. Volcanic soils contain abundant minerals and nutrients, essential for plant growth: phosphorus, potassium, calcium, and trace elements. This fertility has drawn human settlement to volcanic regions throughout history. The slopes of Mount Vesuvius, Mount Etna, and countless other active volcanoes support dense populations and intensive agriculture precisely because the soil is so productive. This creates a difficult calculus. People know the risks, but also rely on the benefits. Generations may pass between eruptions, creating a false sense of security. Communities expand, building homes and farms in areas that will eventually be threatened again. The relationship between humans and volcanoes is ancient and complex, a balance between exploitation of fertile land and vulnerability to catastrophic events. Volcanic eruptions have caused mass extinctions. On a geological timescale, volcanic activity has played a role in some of the greatest catastrophes in Earth's history. The largest mass extinction event, at the end of the Permian period 252 million years ago, coincided with massive volcanic eruptions in what is now Siberia. These eruptions released enormous volumes of lava, enough to cover an area larger than Europe, along with toxic gases and aerosols that warmed the climate, acidified the oceans, and disrupted ecosystems worldwide. More than 90% of marine species and 70% of terrestrial species went extinct. Similar volcanic episodes may have contributed to other extinction events, including the one that preceded the rise of dinosaurs. Even the extinction of the dinosaurs 66 million years ago, primarily caused by an asteroid impact, may have been exacerbated by massive volcanic eruptions in India. These events remind us that while individual volcanic eruptions are dangerous to local populations, the sustained volcanic activity of truly massive eruptions can reshape the entire planet and the course of life itself. Volcanoes helped create Earth's atmosphere and oceans. In Earth's infancy, volcanic activity was far more intense than today. Countless eruptions released gases trapped within the planet's interior: water vapor, carbon dioxide, nitrogen, and other compounds. Over millions of years, this degassing created Earth's early atmosphere. The water vapor condensed as the planet cooled, falling as rain that filled the ocean basins. In this sense, volcanoes are responsible for the very air we breathe and the water we drink. Without volcanic activity, Earth would be a dead world. Volcanism is part of the planet's thermal regulation system, releasing internal heat and recycling materials between the interior and surface. The carbon cycle, which regulates Earth's climate over geological time, depends on volcanic emissions to return carbon to the atmosphere that would otherwise be locked away in rocks. Volcanoes are not aberrations, but essential features of an active, living planet. Mount Etna has been erupting for 500,000 years. Some volcanoes are ancient beyond comprehension. Mount Etna in Sicily has been active for approximately 500,000 years, making it one of the longest continuously active volcanoes on Earth. Ancient Greeks and Romans wrote about its eruptions. It appears in mythology as the forge of Hephaestus, the blacksmith god. Over millennia, Etna has produced hundreds of eruptions, building a massive volcanic complex that dominates the landscape of eastern Sicily. Despite its activity, or perhaps because of it, Etna's slopes are densely populated. Towns and farms cluster on its flanks, taking advantage of the fertile volcanic soil. The volcano erupts frequently, sometimes several times per year, but most eruptions are relatively mild, producing lava flows and ash clouds that are monitored carefully but rarely cause fatalities. Etna is a volcano that humans have learned to live with, a reminder that adaptation is possible even in the shadow of fire. Volcanic islands can appear and disappear within years. The ocean floor is restless, and sometimes that restlessness breaks the surface. Volcanic islands can emerge from the sea during underwater eruptions, building cones of lava and ash that rise above the waves. Surtsey, off the coast of Iceland, was born in 1963 during an eruption that lasted for several years. Scientists watched as the island grew, cooled, and began to be colonized by plants and birds, providing a unique opportunity to study how life takes hold on new land. But not all volcanic islands are permanent. Many are composed of loose volcanic material that erodes quickly under the assault of waves and weather. Some islands appear only to vanish again within months or years. Others last longer, but are eventually reclaimed by the sea. These ephemeral islands are reminders of the impermanence of land itself, of how dynamic the boundary between earth and water truly is. The loudest sound ever recorded was a volcanic eruption. On the 27th of August, 1883, the island volcano of Krakatoa in Indonesia erupted with a force that has become legendary. The explosion was heard more than 3,000 miles away, in places as distant as Australia and the island of Rodrigues, near Mauritius. The sound waves traveled around the globe multiple times, registering on barometers worldwide. It remains the loudest sound in recorded history, estimated at 310 decibels, far beyond the threshold of pain and well into lethal territory for anyone nearby. The eruption collapsed most of the island into the sea, triggering tsunamis up to 120 feet tall that killed more than 36,000 people on nearby coastlines. The atmospheric shockwaves circled the planet 7 times, and the eruption ejected so much ash and sulfur dioxide into the stratosphere that global temperatures dropped and spectacular sunsets were observed worldwide for years afterward. Krakatoa is a name synonymous with volcanic violence, a benchmark against which other eruptions are measured. Submarine volcanoes outnumber those on land. For every volcano we can see, many more lie hidden beneath the ocean. The majority of Earth's volcanic activity occurs underwater, along the 40,000-mile-long system of mid-ocean ridges, where tectonic plates diverge and new oceanic crust is continuously created. These submarine volcanoes erupt constantly, though we rarely notice because they are so deep. The water pressure at these depths prevents explosive eruptions. Instead, lava oozes out, forming pillow-shaped structures as it cools rapidly in contact with seawater. Occasionally, submarine eruptions occur in shallower water, where they can produce dramatic effects. Steam plumes rise from the sea, ash clouds darken the sky, and new islands may emerge. The ocean hides a world of volcanic activity that rivals or exceeds what happens on land, a reminder that most of our planet's surface lies beneath the waves, active and dynamic in ways we are only beginning to understand. Hydrothermal vents support entire ecosystems without sunlight. Where underwater volcanoes and tectonic activity heat seawater, strange chimneys called hydrothermal vents form on the ocean floor. Superheated water, rich in dissolved minerals, pours from these vents at temperatures exceeding 400 degrees Celsius. When the hot water meets cold seawater, the minerals precipitate, building chimney-like structures that can grow many feet tall. Some vents emit black, smoky plumes. Others appear white, depending on the minerals they contain. What makes these vents truly extraordinary is the life they support. In the absolute darkness of the deep ocean, ecosystems thrive around the vents, powered not by sunlight, but by chemosynthesis bacteria that derive energy from the chemical-rich water. These bacteria form the base of a food chain that includes giant tube worms, blind shrimp, crabs, and fish specially adapted to the extreme conditions. The discovery of these ecosystems in the 1970 seconds revolutionized biology, proving that life can exist in conditions previously thought impossible and raising intriguing possibilities about life elsewhere in the solar system. Hurricanes, engines of destruction and heat transfer. Hurricanes are nature's heat engines. At first glance, a hurricane seems like pure chaos, a swirling mass of clouds and rain, wind, and destruction. But beneath the chaos lies order. Hurricanes are heat engines, massive atmospheric machines that transfer thermal energy from warm ocean waters to the atmosphere and eventually to higher latitudes. They form over tropical oceans, where water temperatures exceed 26.5 degrees Celsius, about 80 degrees Fahrenheit, drawing heat and moisture upward in towering columns of convection. As warm, moist air rises, it cools and condenses, releasing latent heat that powers the storm. This energy drives winds that spiral inward toward the center, where they rise again in a self-reinforcing cycle. The hurricane's structure, the eye wall, the spiral rain bands, reflects this elegant but deadly physics. Understanding hurricanes means understanding energy transfer on a planetary scale, the atmosphere's way of redistributing heat from equator to poles. The eye of a hurricane is a calm center, surrounded by violence. One of the most striking features of a hurricane is its eye, a region of relative calm at the very center of the storm. Within the eye, winds are light, skies may be partly clear, and a strange peace descends. But this calm is deceptive. The eye is surrounded by the eye wall, the most intense part of the storm, where the strongest winds and heaviest rains occur. Passing through the eye can give a false sense of relief before the opposite side of the eye wall arrives with renewed fury. The eye forms because of the hurricane's rotation. As air spirals inward, conservation of angular momentum causes it to spin faster, but air cannot reach the absolute center due to centrifugal force. Instead, it rises in the eye wall, leaving a column of slowly sinking air at the center. This subsidence warms and dries the air, clearing clouds and creating the eye. The size of the eye varies. Some are just a few miles across, others more than 40 miles, but the principle remains the same. Hurricane categories measure wind speed, not overall danger. The Saffir-Simpson Hurricane Wind Scale categorizes hurricanes from Category 1 winds, 7,495 miles per hour, to Category 5 winds, over 157 miles per hour. These categories help communicate the intensity of a storm's winds, but they don't capture the full picture of danger. A large Category 1 hurricane can produce more devastating storm surge than a small Category 4. Slow-moving storms can drop catastrophic amounts of rain, causing flooding that kills more people than wind. Hurricane Harvey in 2017 was only a Category 4 at landfall, but it stalled over Houston, Texas, dropping more than 60 inches of rain in some areas and causing unprecedented flooding. Hurricane Katrina's catastrophic impact on New Orleans in 2005 came primarily from storm surge and levee failures, not wind. The categories are useful but incomplete, and emergency managers increasingly emphasize multiple hazards: wind, surge, rain, tornadoes, rather than focusing solely on category numbers. Storm surge can be deadlier than wind. The most lethal aspect of hurricanes is often not the wind, but the water. Storm surge is the abnormal rise in sea level caused by a hurricane's winds, pushing ocean water toward the shore. This bulge of water can reach heights of 20 feet or more, inundating coastal areas with devastating speed. The surge is highest where the strongest winds blow, typically to the right of the hurricane's path in the northern hemisphere. Storm surge can travel miles inland, particularly in flat coastal regions. It can demolish buildings, erode beaches, and contaminate freshwater supplies with salt. The Great Galveston Hurricane of 1900 killed an estimated 8,000 people, most by drowning in storm surge. Hurricane Katrina's surge topped levees around New Orleans, flooding 80% of the city. Storm surge warnings are now issued separately from other hurricane warnings, emphasizing this often underestimated threat. Hurricanes can spawn multiple tornadoes. As if hurricane-force winds and flooding weren't enough, these massive storms often produce tornadoes. Typically, these tornadoes form in the outer rain bands, particularly in the right front quadrant of the storm, as it makes landfall. They tend to be weaker than tornadoes that form from traditional supercell thunderstorms, but they can still cause significant localized damage and occur with little warning. Hurricane Beulah in 1967 spawned 115 confirmed tornadoes as it moved through Texas. Hurricane Ivan in 2004 produced 127 tornadoes across the southeastern United States. These tornadoes add an additional layer of unpredictability to an already dangerous situation, striking quickly and affecting areas that might otherwise escape the worst of the hurricane's impact. Forecasters carefully monitor developing hurricanes for tornadic potential, issuing warnings when conditions favor their formation. The naming system helps track and remember storms. Before hurricanes received names, they were identified by latitude and longitude coordinates, a system prone to confusion when multiple storms occurred simultaneously. In the mid-20th century, meteorologists began naming hurricanes, first using a phonetic alphabet, then women's names, and finally alternating male and female names. Each tropical ocean basin has its own list of names that rotate every 6 years. When a hurricane is particularly deadly or costly, its name is retired out of respect for victims and to avoid confusion in future discussions. Names like Katrina, Andrew, Maria, and Sandy will never be used again. The list of retired names is a somber catalogue of disaster, each name representing a storm that carved its way into history through destruction and loss of life. This naming system serves both practical and memorial purposes. Hurricanes weaken rapidly over land. Hurricanes draw their energy from warm ocean water. Once they make landfall, they lose this energy source and begin to weaken. The friction of moving over rough terrain also slows their winds. Within hours of coming ashore, a major hurricane can be downgraded to a tropical storm. Within a day or two, it may dissipate entirely or transition into a different type of storm system. However, weakening doesn't mean harmless. Even as wind speeds decline, the storm continues to carry enormous amounts of moisture, producing heavy rains that can persist for days. The remnants of hurricanes can travel hundreds of miles inland, bringing flooding to regions far from the coast. The rainfall from these decaying storms can be just as devastating as the wind and surge at landfall, affecting areas that might never experience a hurricane's full fury. Some hurricanes have undergone rapid intensification. One of the most challenging aspects of hurricane forecasting is rapid intensification, when a storm's maximum sustained winds increase by at least 35 miles per hour within 24 hours. This phenomenon can transform a relatively weak storm into a major hurricane with little warning, leaving insufficient time for evacuations and preparations. Several factors can trigger rapid intensification, including very warm ocean water, low wind shear, and humid atmospheric conditions. Hurricane Michael in 2018 rapidly intensified before striking the Florida Panhandle as a Category 5 storm. Hurricane Dorian in 2019 underwent extraordinary intensification, its winds increasing from 150 miles per hour to 185 miles per hour in just 9 hours before devastating the Bahamas. As ocean temperatures rise due to climate change, the potential for rapid intensification is increasing, making hurricane forecasting more difficult and emergency management more challenging. The Atlantic hurricane season runs from June to November. The Atlantic hurricane season officially runs from June 1 to November 30, encompassing the months when conditions are most favorable for tropical cyclone development. The season peaks in late August through September, when ocean temperatures are warmest and atmospheric conditions are most conducive to storm formation. However, storms can and do occur outside these dates, particularly in the modern era as ocean temperatures remain elevated for longer periods. The season's timing reflects the cycle of solar heating. By late summer, the tropical Atlantic Ocean has absorbed months of intense sunlight, raising water temperatures to levels that can fuel hurricanes. As autumn progresses and daylight decreases, ocean temperatures cool and wind shear increases, making conditions less favorable for storm development. Understanding this seasonal pattern helps communities prepare, knowing when to be most vigilant and when the danger has passed. The Great Hurricane of 1780 remains the deadliest Atlantic storm. Long before modern forecasting and warning systems, hurricanes struck without warning. The Great Hurricane of October 1780 swept through the Caribbean during the American Revolutionary War, devastating islands and killing between 22,000 and 27,000 people. Entire fleets of ships, British, French, and Spanish, were destroyed. Communities were wiped out. The storm struck Barbados, St. Lucia, Martinique, and other islands, with winds estimated at Category 5 intensity. The death toll from this single storm exceeded that of Hurricane Katrina by an order of magnitude. It remains the deadliest Atlantic hurricane on record, a reminder of how vulnerable populations were before meteorological science and communication systems could provide warnings. Today, even powerful hurricanes rarely cause such catastrophic loss of life, thanks to forecasting, evacuations, and improved building standards, though the potential for disaster remains. Hurricane Katrina changed American disaster response. When Hurricane Katrina struck the Gulf Coast on the 29th of August 2005, it exposed critical failures in disaster preparedness and response. The storm itself was devastating, but the aftermath was equally catastrophic. Levees protecting New Orleans failed, flooding most of the city. Thousands were trapped in desperate conditions, many at the Superdome and Convention Center. The federal response was slow and inadequate, leading to a national reckoning about emergency management. Katrina killed more than 1,800 people and caused over $125 billion in damage. The storm and its aftermath led to major changes in how the United States prepares for and responds to disasters. FEMA was reorganized, levee systems were rebuilt, and emergency plans were revised. Katrina became a watershed moment, a storm whose name is synonymous with both natural disaster and institutional failure, driving reforms that continue to shape disaster policy today. Hurricanes in the Pacific are called typhoons or cyclones. The storms are identical in structure and formation, but their names differ by region. In the Atlantic and Eastern Pacific, they're hurricanes. In the Western Pacific, they're typhoons. In the Indian Ocean and South Pacific, they're cyclones. All are tropical cyclones, rotating storms characterized by low pressure, organized thunderstorms, and sustained winds exceeding 74 miles per hour. The most intense tropical cyclones on record have occurred in the Western Pacific, where typhoons can reach terrifying intensity. Typhoon Tip in 1979 remains the most intense tropical cyclone ever recorded, with a central pressure of 870 millibars and winds estimated at 190 miles per hour. The storm was also the largest, with tropical storm force winds extending over 1,350 miles in diameter. Regional naming differences reflect cultural and historical variations, but the physics and dangers remain universal. Hurricane hunters fly directly into storms to gather data. To understand and predict hurricanes, meteorologists need data from inside the storms, information that satellites alone cannot provide. Enter the hurricane hunters, crews who fly specially equipped aircraft directly through hurricanes. measuring wind speed, pressure, temperature, and humidity. These flights penetrate the eye wall, often experiencing severe turbulence and winds, exceeding 150 miles per hour to reach the calm eye at the center. The data collected is crucial for forecasting. By measuring the pressure at the hurricane's center and the wind speeds in various parts of the storm, meteorologists can better estimate its current intensity and predict how it might change. Hurricane hunters have been flying these dangerous missions since 1943, and while the technology has advanced dramatically, the basic mission remains the same. Venture into the storm to help protect those in its path. Climate change may influence hurricane intensity. The relationship between hurricanes and climate change is complex and actively researched. Warmer ocean temperatures provide more energy for storms, potentially leading to more intense hurricanes with higher wind speeds and heavier rainfall. Studies suggest that while the total number of hurricanes may not increase significantly, the proportion of major hurricanes, Category 4 and 5, is likely to rise. Additionally, rising sea levels exacerbate storm surge, making coastal flooding worse even if the storm itself is no stronger. Warmer atmospheres hold more moisture, leading to increased rainfall totals and flooding. The rapid intensification phenomenon appears to be becoming more common. While no single hurricane can be attributed to climate change, the trends suggest that the most destructive storms may become more frequent and more damaging in the coming decades. Some hurricanes have lasted for weeks. Most hurricanes have lifespans of less than 2 weeks, but some persist much longer, especially when conditions remain favorable. Hurricane John in the eastern Pacific in 1994 lasted 31 days, traveling 8,000 miles across the Pacific Ocean. It remains one of the longest-lasting tropical cyclones on record. During its journey, John fluctuated in intensity, at times reaching Category 5 strength before weakening, only to re-intensify later. These long-lived storms can affect multiple regions over their lifetime, crossing from one ocean basin to another, or making multiple landfalls. Hurricane Gert in 2017 lasted nearly 3 weeks, affecting the Caribbean, the Atlantic, and eventually influencing weather patterns in Europe. The persistence of these storms demonstrates the sustained nature of the atmospheric conditions that create and maintain them, and the vast distances they can travel across the world's oceans. Tornadoes. Violent vortices. Tornadoes are the most violent storms on Earth. Pound for pound, no storm concentrates more destructive power in a smaller area than a tornado. These violently rotating columns of air extend from thunderstorm clouds to the ground, with wind speeds that can exceed 300 miles per hour in the strongest events. The combination of extreme winds, low pressure, and flying debris makes tornadoes capable of complete destruction, reducing buildings to foundations and tossing vehicles hundreds of yards through the air. What makes tornadoes particularly terrifying is their unpredictability and speed. They can form rapidly, sometimes with little warning, and their paths are erratic. A tornado might destroy one house while leaving the one next door untouched. This capricious nature, combined with their raw power, has made tornadoes objects of fascination and fear throughout history, particularly in the United States, which experiences more tornadoes than any other country. The enhanced Fujita scale measures tornado damage. Since wind speeds inside tornadoes cannot be directly measured in most cases, tornadoes are rated based on the damage they produce. The enhanced Fujita EF scale, implemented in 2007, ranges from EF0 winds, 65-85 miles per hour, to EF5 winds, over 200 miles per hour. Damage indicators, specific types of structures like homes, schools, and towers are evaluated to estimate the wind speed required to cause the observed destruction. An EF0 tornado might peel shingles off roofs and break tree branches. An EF2 can destroy mobile homes and damage roofs of 20-teen, well-built houses. An EF4 levels well-constructed homes and tosses cars through the air. An EF5 represents total devastation, with homes swept entirely from foundations and vehicles thrown more than 100 yards. Fortunately, EF5 tornadoes are rare, but their impact is catastrophic and unforgettable. Tornado Alley experiences hundreds of tornadoes. Each year, a region of the central United States, stretching from Texas through Oklahoma, Kansas, and Nebraska, is known as Tornado Alley. This area experiences more tornadoes than anywhere else on Earth due to its unique geography. Warm, moist air from the Gulf of Mexico collides with cold, dry air from Canada and hot, dry air from the southwest. The Rocky Mountains to the west and Appalachians to the east channel these air masses into conflict over the Great Plains. During spring and early summer, conditions are particularly favorable for severe thunderstorms and tornadoes. Communities in Tornado Alley are accustomed to the threat, with storm shelters, advanced warning systems, and regular tornado drills. The frequency of tornadoes here has allowed scientists to study them extensively, advancing understanding and improving forecasts. Yet despite all preparations, tornadoes remain deadly, unpredictable forces. Most tornadoes last less than 10 minutes, while the most famous tornadoes, those that carve mile-wide paths across multiple states, capture headlines. The majority of tornadoes are much briefer and less destructive. The average tornado lasts fewer than 10 minutes and travels only a few miles. Many are weak EF0 or EF1 tornadoes that cause limited damage and may go largely unnoticed, except by those in their immediate path. However, statistical averages mean little when you're in the path of even a weak tornado. A brief EF1 can still flip cars, tear off roofs, and cause injuries. The short duration also complicates warning systems. By the time a tornado is detected and a warning issued, the event may already be nearly over. This is why meteorologists focus on warning for conditions favorable to tornadoes, rather than waiting to confirm each individual tornado. The tri-state tornado traveled 219 miles in 1925. On the 18th of March 1925, the deadliest tornado in US. History carved a path of destruction across Missouri, Illinois, and Indiana. The tri-state tornado traveled 219 miles over about 3.5 hours, maintaining its strength across an unprecedented distance. It killed 695 people, destroyed 15,000 homes, and left entire towns flattened. The death toll exceeded that of any single tornado, before or since. The tri-state tornado occurred before the modern era of tornado forecasting and warning systems. Many victims had no warning at all. The tornado struck during the day, but its dense debris cloud created darkness like night. Some historians and meteorologists believe it may have been a series of tornadoes from the same storm system, rather than a single continuous tornado. But the destruction was continuous regardless. It remains a benchmark for tornado disasters and a reminder of what these storms can do. Supercell thunderstorms produce the strongest tornadoes. Not all thunderstorms can produce tornadoes. The most violent tornadoes, EF4 and EF5 events, almost always come from supercells. Thunderstorms characterized by a rotating updraft called a mesocyclone. This rotation is key to tornado formation. Supercells form when wind speed and direction change significantly with height, a condition called wind shear. The shear causes the updraft to rotate, creating a storm structure that can persist for hours. Within a supercell, the mesocyclone can tighten and extend downward, eventually reaching the ground as a tornado. The same supercell can produce multiple tornadoes over its lifetime, along with large hail, damaging winds, and torrential rain. Storm chasers and researchers specifically target supercells because they offer the best opportunity to study tornado formation. These storms are relatively rare. Only about 20% of supercells actually produce tornadoes, but when they do, the results can be catastrophic. Tornadoes can occur at any time of year. While spring is peak tornado season in the United States, tornadoes can occur in any month. Winter tornadoes, though less common, do happen, particularly in the southeastern United States. Late-season tornadoes in November and December can catch people off guard, as severe weather is less expected during those months. The famous super outbreak of December 2021 produced dozens of tornadoes, including an EF4 that traveled over 165 miles through Kentucky. The time of day also varies, though tornadoes are most common in late afternoon and early evening when atmospheric instability peaks. However, nocturnal tornadoes, those that strike at night, are particularly dangerous because they're harder to see and because people are asleep, less likely to receive warnings promptly. The unpredictability of timing adds another layer of challenge to tornado preparedness and response. Tornado warnings provide, typically, 10 to 15 minutes of lead time. Modern Doppler radar can detect rotation within thunderstorms before a tornado forms, allowing meteorologists to issue warnings with some lead time. On average, tornado warnings in the United States provide about 10 to 15 minutes of notice. This is a significant improvement over past decades. In the 1,950 seconds, tornado warnings were not even issued publicly for fear of causing panic, but it's still not much time. Those minutes are critical. They allow people to seek shelter, get to interior rooms or basements, and take cover. Schools, businesses, and emergency managers practice tornado drills regularly to ensure everyone knows what to do when warnings are issued. Despite improved warning times and better communication systems, tornadoes still kill dozens of people in the United States each year, typically those who are caught outside, in vehicles, or in structures without adequate shelter. Multiple vortex tornadoes contain several smaller funnels. Some of the most powerful tornadoes are actually composed of multiple smaller vortices rotating around a common center. These multiple vortex tornadoes can be extraordinarily destructive because the smaller vortices, called suction vortices, have even higher wind speeds than the main tornado. As the tornado moves, these suction vortices trace complex overlapping paths on the ground, creating patches of especially intense damage. The appearance of multiple vortices can be striking, with several distinct funnels visible within the larger tornado. This structure tends to occur in the strongest tornadoes, EF4 and EF5 events. Damage surveys sometimes reveal cycloidal marks on the ground, where suction vortices have created their own individual paths. The existence of these smaller vortices within the larger circulation helps explain why tornado damage can be so variable, with extreme destruction next to areas of lesser damage. Waterspouts are tornadoes that form over water. When tornado-like vortices form over water, they're called waterspouts. There are two types: fair weather waterspouts and tornadic waterspouts. Fair weather waterspouts are generally weaker and form from the water surface upward during relatively calm conditions. They're most common in tropical and subtropical waters, including the Florida Keys, where they can occur frequently during summer months. Tornadic waterspouts, by contrast, are true tornadoes that form over water or move from land to water. These can be just as intense as their land-based counterparts and pose serious dangers to boats and coastal areas. Waterspouts have the same rotating column structure as tornadoes, but instead of dust and debris, they draw up water spray, creating a visible funnel connecting cloud to surface. While generally less destructive than land tornadoes due to the lack of structures to damage, waterspouts that move onshore can cause significant damage. The sound of a tornado is often compared to a freight train. Survivors of tornadoes frequently describe the sound as similar to a freight train or jet engine, a continuous, loud roar that grows in intensity as the tornado approaches. This distinctive sound comes from the extreme winds, the debris being carried and ground up within the tornado, and the low-frequency vibrations the tornado produces. The roar can be heard from miles away, serving as an audible warning even when the tornado itself isn't visible. The sound is often accompanied by other auditory cues: the sudden silence when the wind stops just before the tornado arrives, the crackling of power lines, the percussion of debris striking surfaces. In the immediate aftermath, an eerie quiet often descends, broken only by the hiss of escaping gas or the distant sound of sirens. For those who have experienced it, the sound of an approaching tornado is unforgettable, a visceral memory that serves as a lifelong reminder of nature's power. Some tornadoes produce extreme debris clouds. The most violent tornadoes become wrapped in dense clouds of debris, fragments of everything they've destroyed swirling within and around the vortex. These debris clouds can completely obscure the funnel itself, making the tornado appear as a dark, churning mass moving across the landscape. Debris can be lofted to great heights. Paper and other light materials have been found hundreds of miles from their origin. The debris itself becomes weaponry. 2x4s become spears capable of penetrating concrete. Cars become projectiles, weighing thousands of pounds. Even small objects like pebbles or glass shards become dangerous when accelerated to hundreds of miles per hour. After a tornado, the debris field tells a story: objects stripped from one location, scattered across miles. Personal belongings mixed with building materials in a chaotic jumble that can take months or years to fully clean up. Tornado safety has improved, but challenges remain: better forecasting, improved warning systems, and public education have significantly reduced tornado fatalities over the past several decades, despite increasing population in tornado-prone areas. People now generally know to seek shelter in basements or interior rooms on the lowest floor, away from windows. Communities have built tornado shelters in schools, nursing homes, and public buildings. However, significant challenges remain. Mobile homes are particularly vulnerable and provide almost no protection, yet many people in tornado-prone regions live in them due to affordability. Tornadoes that strike at night or are wrapped in rain and obscured from view are more deadly. Urban tornadoes present unique challenges, with high-rise buildings and dense populations. And despite all warnings, some people still underestimate the danger or wait too long to take shelter. Complacency remains a significant risk factor. Climate change may alter tornado patterns. The relationship between tornadoes and climate change is one of the most uncertain areas in climate science. Unlike hurricanes or heat waves, where connections to warming temperatures are clearer, tornado climatology is more complex. Tornadoes require specific atmospheric conditions, and how those conditions might change in a warming world is not straightforward. Some research suggests the overall number of tornado days might decrease, but the number of tornadoes on those days might increase, clustering tornadoes into more intense outbreaks. There's also evidence that tornado activity may be shifting geographically and temporally, with decreases in parts of the traditional tornado alley and increases in the southeast, where tornadoes are more deadly due to higher population density, more mobile homes, and more nocturnal events. The tornado season may be starting earlier and extending later, while individual tornadoes cannot be attributed to climate change. The larger patterns governing when and where they occur may be shifting. Floods. The most common disaster floods kill more people than any other weather-related disaster. Despite their less dramatic nature compared to hurricanes or tornadoes, floods are responsible for more deaths globally than any other type of natural disaster. Flash floods can sweep away vehicles with just 2 feet of moving water. River floods can inundate entire regions for weeks. Coastal floods, driven by storm surge or tsunamis, can strike with little warning. The World Health Organization estimates that floods affect more than 2 billion people worldwide per year. Part of what makes floods so deadly is their frequency and their tendency to strike without adequate warning. A sudden downpour can turn a dry wash into a raging torrent in minutes. People underestimate the power of moving water, attempting to drive through flooded roads, the cause of many flood deaths. And unlike hurricanes or tornadoes, which are discrete events, flooding can be prolonged, trapping people for days or weeks and creating conditions for disease and infrastructure failure. Flash floods can occur with frightening speed. Flash floods are the most dangerous type of flooding. They occur when heavy rainfall overwhelms drainage systems, or when water has nowhere to go, turning streets into rivers within minutes. In urban areas with extensive pavement and poor drainage, flash flooding can occur even from relatively modest rainfall. In canyons and dry washes in arid regions, flash floods can arrive from storms miles away, catching hikers and campers completely by surprise. The power of flash floods is difficult to overstate. Water moving at just 6 miles per hour, a brisk walk, can knock adults off their feet. At higher speeds, it becomes a battering ram capable of moving vehicles, destroying buildings, and reshaping landscapes. The floods often carry debris, rocks, trees, vehicles that adds to their destructive power. Most flash flood deaths occur when people attempt to cross flowing water, either on foot or in vehicles, and are swept away. The deadliest flood in history killed millions. In 1931, catastrophic flooding along the Yangtze River in China killed an estimated 1 to 4 million people, making it the deadliest natural disaster in recorded history. The floods resulted from a combination of factors: abnormally heavy winter snows, spring rains, and summer cyclones that brought relentless precipitation. The Yangtze, Yellow, and Huai rivers all flooded simultaneously, inundating approximately 70,000 square miles, an area roughly the size of England and Wales combined. Millions were left homeless. Crops were destroyed, leading to famine. Disease spread through crowded refugee camps. The economic and social impacts were staggering. While such an extreme event hasn't been repeated, the factors that caused it, heavy rainfall in regions with dense populations near major rivers, remain relevant today. Climate change may be increasing the likelihood of extreme precipitation events, raising concerns about future flooding disasters. River floods can take days or weeks to develop. Unlike flash floods, riverine floods develop more slowly as rainfall accumulates across an entire watershed. Rain falling in tributaries and headwaters flows downstream, gradually swelling the main channel. This slow development can work in both directions for disaster response. On one hand, It provides time for warnings and evacuations. On the other, it means flooding can persist for weeks, keeping communities underwater long after the rain stops. The 1993 Great Flood along the Mississippi River lasted for months, with some areas remaining flooded from April through October. The prolonged inundation caused agricultural losses exceeding $15 billion, damaged thousands of homes, and required months of recovery. River floods also deposit sediment, debris, which must be cleaned up, and can contaminate water supplies. The slow pace of riverine flooding doesn't make it less destructive, just different in character from rapid flash floods. Levees provide protection but can fail catastrophically. For centuries, humans have built levees embankments designed to contain rivers and prevent flooding. These structures protect vast areas and allow development in floodplains that would otherwise be uninhabitable. The United States has more than 100,000 miles of levees protecting homes, businesses, and agricultural land worth trillions of dollars. However, levees create a false sense of security and can fail catastrophically when overtopped or breached. Hurricane Katrina's devastation of New Orleans resulted primarily from levee failures that allowed surge waters to inundate the city. The 2011 Thailand floods killed hundreds and caused over $45 billion in damage when flood defenses were overwhelmed. When levees fail, water pours through breaches with tremendous force, and the protected area floods rapidly. Moreover, levees can increase flooding elsewhere by forcing water into narrower channels, raising levels downstream. The decision to rely on levees involves complex trade-offs between protection and risk. Floods can carry dangerous contamination. Floodwaters are never just water. They carry sewage from overwhelmed treatment plants, chemicals from industrial sites, oil and gasoline from vehicles, pesticides from farmland, and debris from destroyed buildings. Standing floodwater becomes a toxic soup that poses serious health risks. Contact with floodwater can cause skin infections, gastrointestinal illness, and respiratory problems. Contaminated drinking water supplies can lead to outbreaks of cholera, typhoid, and other waterborne diseases. The aftermath of flooding often sees spikes in illness, particularly in developing countries where sanitation infrastructure may be limited. Stagnant water provides breeding grounds for mosquitoes, potentially increasing malaria and other vector-borne diseases. Mold grows rapidly in flooded buildings, creating long-term health hazards. The contamination makes cleanup dangerous and slow, requiring protective equipment and careful disposal of materials. Floodwater should always be treated as hazardous, never as merely an inconvenience. Urban development increases flood risk. As cities expand, natural surfaces that absorb water, soil, vegetation, wetlands, are replaced with impermeable surfaces like pavement and rooftops. This dramatically increases runoff during storms. Water that once would have soaked into the ground now flows directly into storm drains and streams, reaching higher volumes and velocities much faster. Urban flooding has become more common and more severe as a result of this development pattern. The problem is compounded by aging infrastructure. Storm drains designed decades ago for smaller populations and less pavement are now inadequate. Climate change is increasing the intensity of rainstorms, further overwhelming drainage systems. Cities are beginning to implement green infrastructure, permeable pavements, rain gardens, restored wetlands to help absorb water and reduce runoff. But retrofitting urban areas is expensive and slow, and many cities remain vulnerable to flooding from storms that once would have caused little problem. Dam failures can cause catastrophic downstream flooding. Dams serve vital purposes, storing water for drinking and irrigation, generating electricity, and controlling floods. But dams also represent potential hazards. When a dam fails, whether from structural defects, extreme rainfall, earthquakes, or poor maintenance, the results can be catastrophic. The sudden release of the reservoir sends a wall of water downstream with tremendous destructive power. The 1889 Johnstown flood in Pennsylvania killed more than 2,200 people when the South Fork Dam failed following heavy rain. The 1975 Banqiao Dam failure in China killed an estimated 171,000 people, with another 11 million displaced. More recently, the Oroville Dam spillway crisis in California in 2017 required the evacuation of nearly 200,000 people when the spillway began to fail. Regular inspection and maintenance of dams is critical, but aging infrastructure worldwide poses continuing risks, particularly as climate change increases the likelihood of extreme precipitation. Coastal flooding is worsening due to sea level rise. As global temperatures increase, sea levels rise due to thermal expansion of water and melting of land ice. This means that storm surges and high tides reach farther inland than they once did. Coastal flooding during storms is more severe, and some areas now experience sunny day flooding during extreme high tides, even without storms. Low-lying coastal cities and island nations face existential threats as sea levels continue to rise. Miami Beach now regularly floods during king tides, requiring constant pumping and infrastructure improvements costing hundreds of millions of dollars. Pacific island nations like Kiribati and Tuvalu face the prospect of becoming uninhabitable within decades. Bangladesh, with vast low-lying coastal areas and a population of over 160 million, is extremely vulnerable to both river and coastal flooding. Sea level rise is not a future problem. It is happening now, and communities are grappling with adaptation strategies that range from building seawalls to planned retreat from vulnerable areas. Floods can provide benefits, despite their dangers. For all their destructive power, floods have historically brought benefits. Annual flooding of the Nile River deposited nutrient-rich sediment across Egypt's floodplain, making it one of the most productive agricultural regions in the ancient world. Many rivers naturally overflow their banks during wet seasons, depositing sediment that maintains fertile floodplains and replenishes groundwater supplies. Floods also maintain certain ecosystems. Wetlands depend on periodic inundation. Fish in many river systems time their spawning to flood pulses that provide access to floodplain habitats. The problem arises when human development moves into floodplains, turning a natural process into a disaster. Recognizing that floods are natural and, in some contexts, beneficial, has led to changes in flood management philosophy, with some areas now allowing controlled flooding to maintain ecosystem functions, rather than attempting to eliminate all flooding through engineering. Droughts and wildfires. Slow and fast disasters. Droughts develop slowly but last for years. Unlike sudden disasters like earthquakes or tornadoes, droughts creep up gradually. A few weeks without rain is merely dry weather. Months without adequate precipitation begin to constitute drought. Years of below normal rainfall create severe or exceptional drought conditions that fundamentally alter landscapes and societies. Because droughts develop slowly, they often don't command immediate attention, but their cumulative impacts can be devastating. Agricultural droughts affect crop yields, leading to food shortages and economic losses. Hydrological droughts, lower water levels in reservoirs and rivers, threatening water supplies for drinking, irrigation, and power generation. Ecological droughts stress natural ecosystems, killing trees and increasing wildfire risk. Socio-economic droughts impact societies, potentially causing migration, conflict, and even the collapse of civilizations. The slow-motion nature of droughts makes them particularly insidious. By the time the full severity is recognized, the situation may already be dire. The Dust Bowl was America's worst drought disaster. During the 1,930 seconds, a combination of severe drought and poor agricultural practices created the Dust Bowl, one of the worst environmental disasters in American history. Years of plowing up native prairie, grasses to plant wheat, left soil exposed and vulnerable. When drought struck, the topsoil, no longer held in place by deep-rooted grasses, simply blew away in massive dust storms that darkened skies as far away as New York and Washington, D.C. The ecological and human toll was immense. Hundreds of thousands of farm families were displaced, many migrating west to California in search of work, a story immortalized in John Steinbeck's The Grapes of Wrath. The disaster led to new soil conservation practices and government programs to prevent future occurrences. Today, the Dust Bowl stands as a cautionary tale about the interaction between natural climate variability and human land use decisions, and the catastrophic consequences when both align unfavorably. Droughts have collapsed civilizations. Throughout history, prolonged droughts have contributed to the decline or collapse of societies. The Maya civilization in Central America experienced a series of severe droughts between 800 and 900 CE that coincided with its collapse. The ancestral Puebloans abandoned their elaborate cliff dwellings in the American Southwest following a megadrought in the late 13th century. The Akkadian Empire in Mesopotamia fell after a drought disrupted agriculture around 2200 BCE. These collapses weren't caused solely by drought. Social, political, and economic factors also played roles, but water scarcity acted as a trigger or accelerant. When agricultural production fails year after year, food shortages lead to social unrest. People migrate in search of resources, creating conflict. Trade networks break down. Governments lose legitimacy. Drought can push already stressed societies past their breaking point, with consequences that echo through history. Australia's droughts can last a decade or more. Australia is the driest inhabited continent, and droughts are part of its natural climate variability. The Millennium Drought, lasting roughly from 1996 to 2010, was the worst drought in recorded Australian history. Major rivers like the Murray-Darling system experienced severely reduced flows. Water restrictions were implemented in major cities. Agricultural production plummeted, with some farmers abandoning their land entirely. The drought had cascading effects on ecosystems, with many wetlands drying completely and native wildlife suffering population crashes. Lake Eyre, normally a dry salt flat that fills only occasionally, went years without water. When rain finally returned, the relief was palpable, but the damage to agriculture and ecosystems took years to reverse. Australia's experience with extended droughts provides lessons for water management and adaptation strategies relevant to other regions facing similar challenges in a warming world. Wildfire season is lengthening worldwide. Wildfires are a natural part of many ecosystems, but they become disasters when they threaten human communities or when their frequency and intensity exceed natural bounds. Climate change is extending fire seasons by creating warmer, drier conditions that last longer each year. Snowmelt occurs earlier, vegetation dries out sooner, and the window for extreme fire behavior extends from weeks to months. In the western United States, fire season once typically ran from June through September. Now it essentially lasts year-round, with significant fires occurring in November, December, and even January. Australia's Black Summer fires of 2019 to 2020 burned during an unprecedented fire season. The Mediterranean region is experiencing longer, more intense fire seasons. This extension strains firefighting resources and leaves communities vulnerable for longer periods each year. Wildfires can create their own weather. The most intense wildfires generate so much heat that they create their own weather systems. The rising column of hot air, smoke, and gases can reach heights of more than 30,000 feet, forming what's called a pyrocumulonimbus cloud. These fire-generated thunderstorms can produce lightning that ignites new fires, strong winds that spread existing fires unpredictably, and even fire tornadoes, whirls of flame and debris that can move independently of the main fire. Fire behavior under these conditions becomes nearly impossible to predict or control. Embers can be lofted miles ahead of the fire front, starting spot fires that merge with the main fire. Wind patterns shift rapidly as the fire creates its own circulation. Firefighters must retreat to safety zones, unable to directly attack the fire. The 2003 Canberra firestorm in Australia and the 2018 Car Fire in California both produced fire tornadoes and pyrocumulonimbus clouds, demonstrating the extreme conditions that modern megafires can create. Smoke from wildfires affects air quality thousands of miles away. The smoke plume from a large wildfire can travel across continents, degrading air quality thousands of miles from the fire itself. Smoke from western U.S. fires regularly reaches the East Coast, creating hazy skies and unhealthy air quality levels. Canadian wildfire smoke has blanketed American cities. Smoke from Siberian fires has reached Alaska and even crossed the Pacific. The 2020 Australian fires sent smoke plumes that circumnavigated the globe. This smoke contains fine particulate matter, PM2.5, that can penetrate deep into lungs, causing respiratory problems, aggravating asthma and heart conditions, and increasing hospital admissions and deaths. During severe smoke events, air quality in areas far from any fire can become hazardous, forcing people indoors and cancelling outdoor activities. The health impacts extend far beyond the fire zones themselves, making wildfires a regional or even global health concern, not just a local disaster. Some ecosystems depend on fire. Not all fire is destructive. Many ecosystems evolved with fire as a natural and necessary process. Longleaf pine forests in the southeastern United States require periodic fires to clear undergrowth and allow pine seeds to germinate. Giant sequoia trees have thick, fire-resistant bark and cones that open only after exposure to heat. Prairie grasslands historically burned frequently, maintaining grassland ecosystems and preventing tree encroachment. Indigenous peoples around the world practiced controlled burning for thousands of years, managing landscapes and reducing fuel loads. Suppressing all fire in these ecosystems disrupts natural processes and can lead to catastrophic wildfires when fuel accumulates over decades. Modern fire management increasingly recognizes the need for prescribed burns and allowing some natural fires to burn under controlled conditions, though implementing this approach remains challenging when communities are nestled within fire-prone landscapes. The Peshtigo fire remains America's deadliest. On the 8th of October, 1871, the same night as the Great Chicago Fire, a massive wildfire swept through northeastern Wisconsin. The 50 Peshtigo fire killed an estimated 1,500 to 2,500 people, more than any other fire in U.S. history. The fire was so intense, it created a firestorm, with winds strong enough to tear buildings apart and hurl rail cars through the air. Witnesses described the fire as raining fire and creating tornadoes of flame. The exact death toll will never be known because entire communities were incinerated, leaving few survivors to report what happened. The Peshtigo fire has largely faded from popular memory, overshadowed by the Chicago fire that occurred simultaneously. But it stands as a reminder that wildfires can be astonishingly deadly, particularly when they strike without warning and move faster than people can flee. Modern warning systems and firefighting capabilities have prevented similar death tolls in recent decades, but the potential remains. Climate change is increasing wildfire risk. The connection between climate change and wildfires is clear and scientifically well established. Warmer temperatures dry out vegetation, creating more fuel for fires. Earlier snowmelt and longer dry seasons extend the time when fires can ignite and spread. More frequent heat waves and droughts create conditions conducive to extreme fire behavior. The result is more frequent, larger, and more intense wildfires in many regions worldwide. The 2020 wildfire season in California burned over 4 million acres, more than double the previous record. Australia's 2019 to 2020 fire season burned an area larger than many countries. The Mediterranean, Siberia, and the Amazon are all experiencing more severe fire seasons. While individual fires have multiple causes and ignition sources, the overall trend toward more extreme fire weather is directly linked to rising global temperatures. This is one of the most visible and immediate impacts of climate change, turning natural fire regimes into year-round threats. Conclusion: living with Earth's power, natural disasters are part of Earth's dynamic systems. As we've journeyed through earthquakes and volcanoes, hurricanes and tornadoes, floods and fires, a pattern emerges. These events, devastating as they are to human communities, are natural processes that have shaped our planet for billions of years. Earthquakes occur because the Earth's crust is dynamic, constantly moving and adjusting. Volcanoes exist because the planet's interior remains hot and active. Hurricanes form because the atmosphere redistributes heat from equator to poles. Floods result from the water cycle that sustains all life. Understanding that natural disasters are not aberrations, but fundamental features of Earth's systems doesn't diminish their impact on human lives, but it provides perspective. These forces created the world we inhabit, the continents we live on, the soil that grows our food, the water cycle that provides fresh water, the atmospheric circulation that makes our planet habitable. To exist on Earth is to exist within these systems, for better and worse. Human vulnerability has increased. While natural hazards have always existed, human vulnerability to them has grown dramatically. The global population has increased from under 2 billion a century ago to nearly 8 billion today. More people live in coastal areas vulnerable to hurricanes and tsunamis. Cities sprawl into wildfire-prone wildlands. Development pushes into floodplains and onto seismic faults. Population density in hazard-prone areas means that when disaster strikes, more lives are affected. Moreover, modern infrastructure creates new vulnerabilities. Power grids, communication networks, transportation systems, and supply chains are interconnected and interdependent. A disaster in one location can have cascading effects across regions or continents. The 2011 Tonso-Hoku earthquake and tsunami in Japan disrupted global supply chains, affecting industries worldwide. Hurricane Katrina's impact on oil production and refining affected fuel prices nationally. Our increasingly complex and connected society is in some ways more vulnerable than simpler, more localized systems of the past. Yet we have become better at managing risk. Despite increased vulnerability, deaths from natural disasters have generally declined over the past century, at least on a per capita basis. This success comes from improved forecasting and warning systems, better building codes and engineering, effective emergency management, and public education about hazards. Satellite technology allows us to track hurricanes days before landfall. Seismic monitoring networks provide earthquake early warnings. Doppler radar detects tornadoes before they form. These advances save countless lives. Communities in hazard-prone areas have developed expertise in resilience and recovery. Japan's extensive earthquake preparedness, including regular drills and strict building codes, has saved many lives despite the country's extreme seismic risk. The Netherlands has managed flood risk through sophisticated engineering for centuries. California's firefighting capabilities, while strained, represent advanced wildfire management. Progress is uneven and challenges remain, but humanity has demonstrated remarkable capacity to adapt to natural hazards. The future presents new challenges. Climate change is altering the frequency, intensity, and patterns of many natural disasters. Sea level rise increases coastal flood risk. Warmer oceans provide more energy for hurricanes. Extended droughts and heat waves create conditions for more severe wildfires. Heavier rainfall events increase flood risk. These changes are not hypothetical futures. They are occurring now and will intensify in coming decades. Adapting to this changing risk landscape requires sustained effort, investment, and difficult decisions. Some communities will need to relocate from areas that become uninhabitable. Infrastructure will need to be redesigned for conditions beyond historical experience. Water, food, and energy systems will need to become more resilient. International cooperation will be essential as climate-driven disasters increasingly cross borders. The challenges are daunting, but not insurmountable if addressed with urgency and resources. Respect and preparation are key. Living with natural hazards requires a balance of respect and preparation. Respect means acknowledging the power of natural forces and the limits of human control. It means not underestimating risks or assuming that disasters won't happen. Preparation means taking concrete steps, building to code, maintaining infrastructure, heeding warnings, having emergency plans and supplies, supporting investments in resilience. Communities that respect natural hazards and prepare appropriately fare better when disaster strikes. Those that ignore risks or assume technology will save them without effort often suffer more. The relationship between humans and Earth's powerful forces is ongoing, requiring constant attention and adaptation. Complacency invites tragedy. Thoughtful preparation enables survival and recovery. Our stories shape our response. How we talk about natural disasters matters. Viewing them as acts of random malice or divine punishment leads to fatalism and paralysis. Understanding them as natural processes that can be studied, predicted to some degree, and prepared for empowers action. The stories we tell about disasters, stories of resilience, of communities coming together, of learning and adapting shape how we respond to future events. The narrative of disaster also affects policy and investment. When disasters are seen as rare anomalies, societies underinvest in prevention and preparedness. When understood as inevitable aspects of living on a dynamic planet, the case for sustained investment in resilience becomes clear. Changing these narratives is part of the work of building safer, more resilient communities. there is beauty in understanding. As we come to the end of this journey through Earth's most powerful forces, perhaps you find yourself with a different perspective. Yes, natural disasters bring destruction and suffering, but they also reveal the extraordinary processes that shape our world. The energy that powers an earthquake is the same energy that built mountains. The heat that fuels volcanoes created the ground beneath our feet. The atmospheric circulation that generates hurricanes distributes heat across the planet, making much of Earth habitable. Understanding these connections doesn't diminish the human cost of disasters, but it places them within a larger context, one where destruction and creation are intertwined, where the same forces that threaten us also sustain us. There is a certain peace in this understanding, a recognition that we are part of something vast and ancient, processes that were occurring long before humans existed and will continue long after. Rest in the knowledge. And so, dear listener, as we conclude this exploration of Earth's power, I invite you to rest. Rest in the knowledge that these forces, awesome and terrible as they are, follow patterns we can understand. Rest in the awareness that human ingenuity and cooperation have made us more resilient than ever before. Rest in the perspective that comes from seeing our place within geological time and planetary processes. The ground beneath you is ancient and ever-changing. The atmosphere above you is in constant motion, redistributing energy and moisture. The water that flows through rivers and oceans has been cycling through Earth's systems for billions of years. You are part of this living planet, subject to its rhythms but also capable of understanding and adapting to them. As you drift toward sleep, imagine yourself from above, a small part of this vast, dynamic Earth. Feel the stability of the ground, solid despite its gradual motion. Feel the gentle movement of air, powerful when concentrated but normally a soft breeze. Feel the presence of water, vital and life-giving even when occasionally destructive. Natural disasters are part of the story of our planet, chapters of violence in a longer narrative of creation and change. Understanding them brings not fear, but perspective, a recognition of what is within our control and what is not, what we must respect, and how we can prepare. Sleep well, knowing that Earth's forces, for all their power, have shaped a world capable of supporting life, including yours. Rest in the stability of billions of years of planetary evolution, in the resilience of ecosystems and communities, in the ongoing human project of learning to live wisely on this dynamic, beautiful, and sometimes fierce world we call home. Good night.